keyword. So welcome to the seminar of the SONY Astani Department of Civil and Environmental Engineering. So today our speaker is Christopher Boxe. So let me tell you a few words about Christopher. Christopher was born in Jamaica and went to get his BS in chemistry and a minor in math in Morehouse College. He got his degrees in 1999 with honor from Phi Beta Kappa. Then he went to Caltech and graduated from Caltech with an MS in planetary science and also a MS in environmental science and engineering, and then a PhD in environmental science and engineering. That was in 2005. He completed, I think now, he has completed a 3 years postdoc at JPL Earth and Space Science Division, and for the last year he has been a research scientist at JPL doing work with Earth-based satellites and planetary science teams. His research interests are broad and interdisciplinary in nature, with a general emphasis on the evolution of planetary biospheres. Christopher, the floor is yours.
Oh, thanks.
So, get that. It's basically much used to, like you're
Yeah, thanks you to the great introduction. So today I'll give an overview of the implications of what this title illustrates here. And in a sense, it's TES is a satellite, an instrument actually on board one of the NASA satellites called Aura. It was launched in 2004. And the TES stands for Tropospheric Emission Spectrometer. And it measures, does global measurements, vertical profiles of aerosols, trace gases globally, and it's been doing that for the last, since 2004 of its launch. But the primary bulk of the talk will comprise the implications of the latest validation study. So when a satellite measures a specific species, such as ozone, they call this a data product, and they better quantify this data product as the years progress. And they have to validate that data product with in situ measurements from, for instance, ozonesondes for various species, or airplane measurements. So the community can say, oh, if you're going to assimilate this, for instance, ozone into a model to make a prediction of the evolution of ozone, for instance, over the week in Los Angeles, people actually trust that prediction. And I'll end the talk with a few slides describing the implications of this validation study, but in a specific sense for ozone, but the implications of actually utilizing satellite data to coupled with a high-resolution model to say something about the dynamics of ozone in the stratosphere and troposphere, and also the evolution of air pollution on a localized scale, regional scale, and also radiative forcing effects that are pertinent for climate change issues. But before I actually go into the talk, I wanted to give a brief kind of overview in the next couple slides, 2 to 3 slides, of my overall research focuses, and the percentage of my time, of course, is weighted differently depending on the projects you see here. So one of them is in the area of renewable energy, sustainable energy, and this is a collaborative project with my former advisor at Caltech, where we're looking at different photocatalysts to sequester is a kind of a funny word, but we're actually converting CO2 and trying to formulate formulate most efficiently renewable energies, and then in that process also utilizing these same procedures, see how these procedures can be coupled to novel wastewater treatment techniques. And this is actually very novel in the sense that, of course, this field, people have looked at it not necessarily for CO2 sequestration, but it's novel in the sense that we're coupling it with looking at protein amines. which a lot of groups haven't done so far, as electron acceptors, and to increase this efficiency. So, and the third is a kind of steady state, sustainable work that is fairly in motion. It's very easy for me to do, is that I utilize various models, one-dimensional models, box models, and global models, and I work with a lot of satellite data, primarily for Mars and Earth. The main focus has been on Earth, and some of this work actually I'm doing in conjunction with people here at in the Earth Science Department, and really to look at to really define where you find life on a particular planet, and also to look at new chemistry on different planets. So I've developed software with international collaborators to apply this to different model outputs. So, and then thirdly, these two are actually interrelated, is that the experience that I've had in the last year and a half, I've looked at a lot of satellite data. So for the test data, the test team, I'm actually a person that deals with anything related to ozone. And but I've also worked with the temperature data product and also the water data product. And the primary goal is to actually make sense of a lot of the satellite data. There's a ton of satellite data and a lot of people don't use it, but the idea is to really take that in motion with a fairly new community model, which was built primarily, not good. Wow.
Technical support has vanished.
Yeah, I apologize about this.
Thank you. No problem.
Yeah.
We didn't plan to trip you.
Oh, no, it's okay. So we were right where we started. Saying something about, so utilizing this model to to interpret that data in a usable form for climate change issues and forecasting issues. And then I also do a lot of work in terms of education and education and public outreach. And one of the primary focuses now is, since I've maintained a strong relationship with my former undergraduate institution, Morehouse College, in the midst of writing a fairly medium-sized proposal for NASA, where we'll utilize this model, this weather research forecasting model, and its radiative forcing subroutines and chemistry subroutines as a platform for undergraduates to learn science. And so that's research call related for that. But this is exciting in the sense that it can be provided as a basis for a bigger kind of conglomerate proposals, such as the NASA Advanced Grants or IGER grants. So getting back to the task at hand, so what is actually involved in validating satellite data, such as the ozone data product? So before I get into the actual details of that, I wanted to give all of you an overview of just how NASA operates in terms of satellite data. And NASA started this initiative called, and the top of that initiative is called the Earth Enterprise. But so below that, they started to launch a series of satellites, which are part of the Earth Observing Satellite. And this satellite here is just one of them, called Aura, where TES is a part of. And they utilize various techniques, either probing the atmosphere straight downwards, or which is called a nadir, or probing the atmosphere from the side views angle, which is called a limb measurement, to gain an understanding of chemistry, dynamics, and then coupling that with models to do predictability and so forth. So Aura actually measures pretty much anything you can think of, from aerosols to all the important greenhouse gases, trace gases. So just with this satellite, you can actually get a lot of science out of it. So I just included this slide just to show you that with just this particular satellite, and the science enterprise from NASA actually is comprised of, right now, over 30 satellites are doing similar things. So there's a lot of data to actually make a good case for science. So this slide, I just wanted to illustrate and emphasize that AURA, the satellite the tropospheric emission spectrometer is actually a part of, which is shown here, is a part of what we call the A-train satellites, and these are called low orbiting polar synchronous, sun synchronous satellites, which means that they orbit at about 400 miles in the atmosphere and they cross the equator about the same time. That's what the A is for afternoon. It's about 1 p.m. every day. And the nice thing about these satellites is that they're about plus or minus a few minutes apart from each other. So they actually give a complementary description of things related to climate change issues and dynamics and anything you could, like I stated before, think of related to chemistry and dynamics. So there's a lot of data out there. And I'm sure all of you know about OCO. This is actually not up yet. It was launched last year in February, but the launch failed and it landed in the Antarctic Ocean. But importantly is that it's, science continues and you pick up where you left off, and JPL is actually doing the rebuilding now. And it's supposed to launch in about 2.5 years, 3 years time scale. So the great thing about this is that although you actually have a satellite now, this is a Japanese-based satellite called GOSAT that measures CO2 profiles globally. The great thing about this was that the resolution, so GOSAT would be kind of parallel to what a GCM model, a global circulation model is. The resolution is very coarse, but OCO could actually say, pinpoint USC and say, USC, this is your carbon footprint, and how it distributes as a function of altitude. So the resolution would be very applicable and very important for kind of simulatory science and predictability to constrain the influence of CO2 on radiative forcing on various timescales. So that's why it was a big, I didn't see anyone cry from Caltech or JPL, but it was definitely a down time, but things are looking up. And like I've stated previously, all of these activities are a part of the Earth Science Enterprise, which NASA spearheaded in the mid-1990s. And this just shows you that there are many satellites a part of this effort, and a lot of coordination is involved through North America, Asia, and Europe. So what I'll go over today is what's the big motivation for actually looking at validating, for instance, ozone, one of the data products of the TES instrument, and why is TES, why should we care about it? How's this work actually, how does TES actually work? How do we actually do the validation work? And what's the difference between this validation work and previous studies? And the quantifiable products, such as something that's never been done before. We use a special observation technique for this satellite where we stare, for instance, let's say at USC or a really small footprint compared to a more coarser footprint, and we're able to do something that's never been done before for any satellite, is quantify the errors that we actually theoretically predict for the instrument in terms of the actual errors for that instrument, amongst other quantifiable products such as the bias, which compares to what we're validating it to the ozone sondes, and what's the sensitivity of our instruments as a function of altitude. So what's the motivation for doing this study? So I stated that the TES was a part of the AURA satellite, which was launched 2004, and these two studies, these 2 points actually kind of go together. So from 2005 to 2006, there was a first validation study conducted, and this was for the first couple years of the TES data, which had some degree of uncertainty, but we still had to validate it regardless. And so the primary goal is that this is the latest data product, what we call version 3 and version 4, and this is more well characterized, because when you're actually doing a remote sensing, this is a Fourier transform infrared spectrometer. You're looking at the actual radiance or the heat emitted from the surface that's backscattered through the atmosphere, and one of the biggest uncertainties is how do you discriminate between that signal due to temperature and pressure differences as it propagates from the surface to the atmosphere. And this is well quantifiable in the latest two versions. So, but more importantly, we're motivated to quantify the biases and the theoretical and empirical errors, which was the first done for any satellite remote sensing technique. And that's really due to this low footprint mode, this what we call the stare mode. And so for instance, so what the stare mode means is that if I'm looking at the audience, I can't really tell you, the uncertainty that I can tell you of where someone is looking is probably larger if I'm just looking at, for instance, Joseph Davini, right, instead of like probing the entire audience. So it's kind of a general sense, that's what it's doing. And secondly, I stated that there's sensitivity issues, which increases the uncertainty of this retrieval method. And this increases with latitude because of kind of isothermal effects with the surface and the atmosphere. But these characterizing that was been well parameterized. So we're able to do one of the first validation of a high latitude data product via this remote sensing technique. So why do we care about ozone? And this is a refresher for everyone. And this is, of course, ozone in the lower troposphere, the boundary layer, is mostly concern for air pollution studies, is that it's air pollutant. It can cause respiratory problems, headaches, etc. And in the middle of the atmosphere, it's actually a good thing because it's an oxidant. It actually cleans the atmosphere. But then as you get higher, and this is a kind of a trend that's one of the things I'm looking at is the increase, what's believed to be the increasing trend in tropospheric ozone or high latitude or high altitude ozone. And the reason why that's important is that this can contribute more to the radiative forcing or the warming of the planet. So I'm doing a project in conjunction with NCAR and JPL and UC Boulder to use different tracers to try to figure that problem out. And of course, this is important for the stratosphere as well, although a lot of the work that I've done isn't really relevant to the stratosphere. But to give you a global context, this plot here is a function of year versus ozone, and the pink plot is a modeled plot where you kind of have a prediction of how ozone is going to actually recover from the time of the Montreal Protocol, where after that, the use of CFCs or long-lived chlorine compounds that were destroying the ozone layer were banned. And getting all that science together and you plug it in a model, you realize that the ozone will, at least that's what this model predicts, will recover. But measurements actually show that ozone is actually recovering. And this is just shown here from a plot from an instrument called HALO. And actually, another instrument on the ORA satellite is actually showing that it's actually decreasing as well as a function of time. And the instrument on ORA is called HURTLES. It's measuring HCl. And the reason why HCl is important is that you can show it is because it's one of the primary reservoirs for long-lived chlorine species that gets into the stratosphere and then contributes to the destruction of ozone. So why is TES a novel satellite? TES is a novel satellite is due to the fact that primary to the launch of TES, most instruments actually gave you a bulk measurement. So they were only able to say that the amount of ozone is X throughout the entire atmospheric column. And that's pretty much, that's very useless if you want to couple that with the model and do predictability studies and also do radiative forcing studies. since you would need a kind of vertical measurement, for instance, if ozone is radiative-forcing gas or greenhouse gas in the troposphere. So it's novel in the sense that it measures vertical profiles of ozone and other species for the first time. And then it provides, of course, a global kind of perspective of that as well. And how does TES work? So I thought to illustrate this in a simple kind of plot, a simple kind of picture is that it's a Fourier infrared transform spectrometer, and it primarily splits a sunlight or, as a function of pressure and temperature, and then recombines that light and gives you an interference pattern. But in any case, it gives you a pattern that's representative of the molecule decoupled from the atmosphere, which is a signature for any species as a function of pressure and temperature. And then you have a quantifiable product as a function of altitude. And the great thing about this instrument is really how the engineers, I mean, this is kind of beyond kind of the hardcore engineering, is how they actually built this instrument to have such high sensitivity. And high sensitivity, and this plot is pertinent to the the planetary boundary layer. So this is a plot that represents wave numbers. And on the y-axis you see radiance. But the take-home message of this plot is this is a pressure broadening plot, what you would see for ozone at this resolution, at 0.6 wave number resolution, versus a much higher resolution. But as you see here in the black bold is that these are the resolutions for the TES instrument. So regardless of the extreme, well, not extreme, but the pressure broadening that's experienced by ozone on the surface, TES is actually able to discriminate that and tell you something that's quantifiable and trustworthy for many species, not just ozone. And this is just a reinforcement kind of schematic, is that as TES measures in two modes, one looking downwards and then one looking through the sideways view. So the mode looking downwards has the lower resolution because you're sampling less of the atmosphere. So at most, that gives you a vertical resolution of about 6 kilometers and a footprint of about 5 by 8 kilometers. But of course, with the limb mode, which is a kind of side view mode, you're measuring a large portion of the atmosphere, and that gives you a much higher resolution of about 3 kilometers and about 2 to 5 kilometer footprint. But since 2005, the team actually had to eliminate this kind of most of the limb measurements due to instrumental issues, and this actually increased the lifetime of the instrument, so it's still flying. So those are the instrumental modes for observation. So what's the role of sondes? Of course, as I've stated, if you send a balloon up and you have a satellite orbiting a planet, you want to know if the data is trustworthy. So this is a kind of a big effort, especially with this study, because we had to coordinate with people from Environmental Canada and several universities in the United States, and coordinating a specific launch with the overpass of a satellite just to say that, you know, we're measuring this sample of the atmosphere at this time, and you need to launch this product at this time, and with, you know, reasonable coincidence compared to previous studies, which had like 2 days, you know, time separation, several 100-kilometer time separation. And these days, actually, ozone sondes have reasonable precision and accuracy, so they're very trustworthy tools for validation. And a little chemistry, because I'm a chemist. I don't know if anyone cares about this, but the way a sonde works is that you have variable sondes, but the most common ozone types of sondes is a platinum electrode, where you have 2 baths and you have an ion bridge, and then your species actually enters and then reacts with your buffer solution. In this case, it's potassium iodide. And that species actually induces an ion current, which can then be quantifiable to the partial pressure of your product, which is ozone in this case. And you have all the variables measured. You have the temperature, the time for the measurement to be taken, the ion current, and then this produces a mixing ratio or number density, whichever you like, of that product. So what's the difference between this validation study and previous validation studies is that, yeah, of course I'm validating the latest two versions of the data product, but primarily the most important take-home message is that you know, I really wanted to use my own laptop because I had two movies to kind of illustrate kind of this this idea in a sense, but I'll just have to explain it in words. Is that there are actually four observation modes for the TES instrument, right? So one observation mode is the observation mode used in this paper, this investigation, which is now in press, is the stare mode, just looking at you and saying something about the comparison with the ozone sonde. But then you have another mode, which is called the global survey mode, where TES is actually just mapping the Earth. It does 16 orbits in about 26 hours, and it's all nadir view, just looking straight downwards. And it does that and repeats itself after about every 16 days. So you get about 233 sampling retrievals in that time frame. And then you have what you call the transect mode, which is for special events. And one special, most recent event was the Summer Olympics in Beijing, China, where you get you scan over a really kind of 45-kilometer footprints, and by 45-kilometer footprint, by 40-kilometer footprints, and then you do it again, and then you say something about the atmospheric composition at a specific point in time. But then you have the step and stare mode where you do this but on a longer time frame. So, but the take-home message of this slide is that, stated previously, is that previous studies had these huge disparities between the time coincidence. So you had 2 days to some extremes to several hours, and the spatial difference were much larger instead of kilometer spatial difference, and less than an hour or so time coincidence. And this plot is just a function of latitude versus pressure, and this is just a sample of the stare mode. And what it actually does is it looks at a point and it stares. It actually takes 33 retrievals or 33 samples of that specific point within about a minute and a half, 2 minutes. And what I just wanted to illustrate here is that the latitudinal difference is so small that the footprint, when you do the calculations, it shows you that the footprint is about a kilometer by a kilometer or even less. And this slide is just to reinforce, these actually show all of the coincidence measurements that were done. They were done from about 44 degrees latitude all the way up to the highest latitude, which was about 71 degrees north latitude in Barrow, Alaska, where you see a time coincidence from about a few hours here, 3 hours, to down to fractions of an hour. So this was very important because for people who appreciate some statistics, this actually able to really quantify the errors on our own instrument because of smaller differences between the root mean square error and the actual ozone sonde root mean square error. So how do we actually make sense of the data? So when comparing a sonde to an actual TES retrieval, we use what we call the TES operator. And what the TES operator actually is comprised of is comprised of a weighting function called the averaging kernel. And this averaging kernel is produced from the Langley data center, and the a priori profile, which is produced from Mozart, which is called the model for ozone and related tracers, as our initial boundary conditions. And it gives you a profile, so we're not comparing apples and oranges. It gives you, it produces a profile as if the instrument was actually sampling the same IRS parcel that the ozone sonde was sampling. So you're actually on the same wavelength. But more importantly, just a caveat is that in doing this, we actually are able to relate the ozone sonde measurements, which are on a kind of a really fine grid. Remember I stated our resolution is about 6 kilometers for the nadir view. So the ozone sondes have measurements for about fractions of a kilometer or every few meters. So we actually have to interpolate that and transform that data on our coarser matrix. So I stated, this is a kind of a novel study in a sense, is that we were able to quantify our empirical, theoretical errors to the empirical errors. And this first line shows you, this is from satellite retrieval estimation theory. And the main take-home message of this slide is that one can estimate the matrix that represents a satellite retrieval by various functions here that are weighted by the averaging kernel or the sensitivity or the weighting function for that retrieval. The model radiance, or the matrix that represents the radiance or the sunlight that's retrieved from the model, and parameters that are affected by the forward model. And then one can assume that this estimate is a real representation of the retrieval. If you take the difference here, then one produces an error kind of representation where you have a smoothing error and the measurement error and the systematic error. And so the smoothing error really describes the transforming, kind of interpolating coarser grid data of not only the ozone sonde but the TES retrieval on a quantifiable matrix grid. And then this represents errors in the spectra that are a function of the forward model. And this also represents errors of transforming the forward model on the full state vector, or the true state vector. And then, so this is how we actually quantify our actual retrieval. But then we are able to quantify our biases as well. So the differences between the actual satellite retrieval and the actual TES retrieval. And the nice thing is that this is done in a way that it's not biased by the a priori or the profile that's produced from the GCM Mozart. But all this you can forget, so it's not so important. So in the next couple of slides, I'll spend a few minutes really describing, I highlight two cases, right? So in the first case represents the lower latitude case, which is I don't remember which one I did first, but one of them represents a lower latitude case, 44 degrees north latitude, and that's of Egbert, Ontario, or Egbert, and then the Barrow, Alaska, which is a 71 north degree latitude. And these are just the spatial kind of representation of the measurements. This is Egbert, and this is Barrow, Alaska. And what you see here on the top left panel are, you have 4 plots, and these are plots of the top left panel here represent the actual mean TES retrieval. So we average the retrievals for the TES ozone profiles as a function of altitude, and that's represented on the black line. And then the actual explicit sonde data, and then on this kind of, I don't know what color is, magenta, is the line, the profile that's produced by applying the TES operator. So representing the TES retrieval as if it was sampling the same air as the sonde data, and then the dashed profile is the actual profile given to us by the Mozart GCM model. And what you see here, despite some variability when applying the from the actual sonde data, you see that there's a great coincidence with the measurements. So we know that even using this kind of explicit stare technique, that it validates previous studies, and the TES data product for this version, both versions are actually very valid, right? So the plot on the top right explains the sensitivity of our instrument. So this is pressure as a function of a weighting function. And what this shows you here is, it really shows you how sensitive a test retrieval at a specific altitude is to the dynamics and chemistry of ozone and other variability at all other pressure levels. So for the black line here, this is for plots less than 400 hectopascals, so below the mid-troposphere. You see that you have some sensitivity, let's say right here, towards ozone at other pressure levels contributing to that test retrieval. So, and then we are able to quantify our biases, and in general, I mean, there's some disparity when looking at specific plots, but in general we see high bias, kind of a positive bias compared to the sonde measurement in the troposphere, the low to mid troposphere in general, and a negative bias from the low stratosphere to the mid stratosphere, which validates previous validation studies and actually current studies that are in press now. And this is kind of the novel take-home for the investigation, is that not only our biases are, at least in the satellite community, is within a respectable kind of quantifiable agreement, less than 20%, but the empirical and theoretical errors overlap very well as a function of altitude, but are also respectable in terms of their percent, and at most 15% of errors. So similarly for Egbert, we see a same kind of qualitative congruence between the actual explicit satellite data, the mean TES ozone, average test retrieval, the test operator profile, and the a priori profile. But the nice, I showed this plot for not just to represent the lower latitude kind of coincidence measurement, but also to show you, which was very important for the test instrument, is that given its resolution, the weighting function shows you that at various altitudes you still have sensitivity to actually retrieving ozone and the planetary boundary layer, which is what this take-home message of this plot is. And similarly, you see kind of a positive kind of bias in the troposphere, and as you go higher, you see a more progression towards a negative bias in the stratosphere, and congruence within in terms of the theoretical versus empirical errors, which are slightly acceptable here. But in general, we're able to see agreement between both quantifiable error products. So, in conclusion, and after this slide, I'll briefly describe the implications of this work. We are able to validate the latest two ozone data products, which are the most well-parameterized and characterized data products for ozone to date. And but more importantly, the study represents the first validation of a satellite data product at high latitude. And this is important because if the physics are actually get a little bit better, we can, even reevaluate previous data sets for not just ozone, but various satellite data products, and actually utilize some of that satellite data, let's say for the polar regions, where a lot of the climate modeling had the highest uncertainty, right? Because some of the data they used to assimilate into their models had huge uncertainties in those regions. And that's a direct result of some of the uncertainties in some of the satellite retrieval products. And then, of course, the theoretical and empirical errors overlap, but they're in a reasonable, acceptable agreement and range, less than 20%. And the biases are usually positive in the troposphere, but approach a negative direction in the lower strat to mid stratosphere. So why should I care, or should anyone care about this? Is that I applied for a proposal last year, this new investigative proposal. So I care a lot about satellite data. And the reason being is that I think, at least for my near future, apart from the planetary modeling and planetary experimental work that I'm involved in, and the collaborative work with my advisor in terms of CO2, I would call it more CO2 conversion chemistry, photoelectrochemical chemistry. I think the primary kind of research base that I'm going to be heading towards is, utilizing the huge database of huge satellite database that's available to say something about the dynamics of trace gas species, especially ozone, on the lower stratosphere, upper troposphere, which is a very hard, very difficult problem. It's a hard problem to quantify. And try to say something about that, and then also using the subroutines of this weather research forecasting model and chemistry subroutines to say something not only in the higher altitudes, but looking at transport of aerosols, for instance, air quality, but then also looking at extreme events such as the North American monsoons and the Asian monsoons, and how that affects chemistry and transport, Eastern Asia and Eastern China. And those are two big uncertainties now, and how that ties into the radiative forcing of trace gas species such as ozone, and how that relates to climate model prediction. And then a subset of also that work is on the finer resolution scale, how can the satellite data be assimilated into a forecasting model such as this one to say, to a better degree, which decreases the uncertainty when you have a high resolution model such as this on fractions of a kilometer. You can get how can the satellite data be used to better forecast dynamics in chemistry? And I think this is kind of reinforcing kind of the bulk kind of climate change question. So I wanted to, of course, thank everyone, and I apologize about that. Thank everyone for listening to me today and inviting me to talk, and JPL for funding me for a lot of these things and getting me prepared. Any questions? Thank you.
So, any question for Christopher? Yes, Joe.
Can you explain to us again how it is that the instrument measures ozone concentrations at different levels in the atmosphere?
I skipped too fast. But while I'm doing this, so what it does is they have two measurement modes. You have what you call the nadir mode, which is the vertical viewing mode. And that has the lowest resolution. As I stated, it's sampling less of the atmosphere. And then you have the side view, semi-side view mode, and these angles can change. So you kind of have pseudo limb view measurement and then pseudo kind of nadir view. But in general, so what it does is that it's a Fourier infrared transform spectrometer. So anything that's above the absolute zero has a certain signature. So let's say I'm at 290K and I'm at 298 Ks, and then I'm at the surface pressure. So I have a signature of beta, and that beta can be represented in terms of a certain spectra, right? As a function of pressure and temperature, which is directly a function of the radiance or the sunlight that's retrieved from the satellite. And so the satellite is able to decouple that information from the actual spectra that's known for the atmosphere as a function of pressure and temperature. And you compare it with a known database for various species as a function of pressure and temperature. And this is done well before the actual satellite is launched. And it compares that database, and then you're able to know the concentration of that species based on that spectra and known pressure and temperature spectra from FTIR experiments. So, and this is done Yes. That's pretty much how it's done.
Okay. Thank you.
I have a question, Christopher. Just going back to your graphic here. Your satellite is at 100 miles, right, from this Earth surface.
Yeah.
The probe that we launch, which is Berlin, is reaching a certain altitude. What altitude usually the probe will reach? That probe usually carry an instrument, right?
Right, and also the ozone sonde, right?
So I'm just curious, we're comparing satellite is going to send a beam
Yes.
downwards, and beam is going to be reflected, and we collect all kind of absorption along the trajectory. I'm curious, what are we comparing between, what segment here on this are we comparing?
Right, so the satellite, that's a good question, so the ozone sondes are launched from the surface of the Earth, and they reach about 35 kilometers at most.
35.
Yeah, depending on the latitude, it's the mid or kind of low mid actually mid stratosphere, excuse me. Yeah, so about the mid stratosphere in general.
20 miles.
Yeah.
Compared to 400 miles.
Right. Yeah, it's about 1.6. Yeah. So, and sometimes they burst and sometimes they fall, and so usually the measurements stop after that 35 kilometers. Yeah.
And so far the measurement has been in the ozone. Do we have all the type of measurements, just like for particulate matters, like aerosols and so on? Because there's a lot of now work being done using aerosol, measuring particulate matters 2.5, and PM 2.5. So I'm curious if we could have comparison between a balloon, which is actually have a much accurate, it's a direct measurement, right?
Yes.
It measures actual signals,
right,
compared to a satellite, which has an interpreted signal. It's
right,
using absorption, it's using a different type of devices, right?
Right.
So I'm curious if we could attempt this direct comparison. But of course, the satellite can give us broader horizon measurements. The balloon is a very linear segment of measurements. So I'm worried that if we had at least already these comparisons, and what would be the difficulties in creating these comparisons?
I don't know of any, unless, this is something I don't know if they have actually in situ kind of measurements on balloons for aerosols. I mean, it's a very good question. I know most of the aerosol community, they do field campaigns from, many places, and kind of ground-based measurements of aerosols. But I don't think it would be beyond the realm of possibility to do something like that with a particular kind of instrument, such as an ozone sonde. But that's something I'm not keen on, or at least I'm not aware of. But I mean, for instance, when you the TES, but primarily hurdles and MLS, microwave lymph sounded, that measures aerosols, that's one of the issues. They don't have a lot of in situ data to actually validate some of the measurements with. So, I mean, people just assume it's true, but it's a good point.
Do you have more questions? Yes.
What other kind of applications do you see for TES instrument for a modification in general?
I think that the TES instrument, once it actually fails, I think it's actually approaching this right now. I think part of the team is really they're working with the Japanese team and actually the OCO team to better, since TES is a great instrument because of the sensitivity issues. So one of the advantages of TES is that is to actually increase the resolution of OCO, because TES actually has a better resolution than what OCO would have had. So a lot of the physicists in the TES team are actually working with GOSAT and the OCO team to actually apply some of these same kind of fundamental principles. This kind of high-level physics that's kind of beyond me. But that's definitely one of the advantages, and that's one of the things that people are doing now. to actually look at the sensitivity issues and better characterize the surface. If you can even, I don't know if it's possible, even make instrument even more sensitive than 0.025 wave numbers, for instance, for CO2. So that's one primary kind of thing that people are looking at, and that's applicable for decreasing the uncertainty for CO2. CO2 retrievals at high latitudes, for instance, where polar kind of radiative forcing is a big question in terms of trusting it from a climate model. So.
Do we have more questions? Yes, Rod?
Is there any overlap between the old TOMS data and TES and how they compare?
Total ozone spectrometer. The TOMS data, as a function of like spatial comparison, they compare fairly well. If you can integrate the total column for the test data, they compare fairly well. So yeah, there's really no discrepancy there in a general sense, but as far as I know about that.
So, Ron, can somebody explain what is TOMS?
Sorry, I should repeat the question. So
total
the question,
ozone monitoring.
how does the tropospheric emission spectrometer compare with the total ozone macro spectrometer? And this is a spectrometer was similar to the ozone monitoring instrument, where they only produced integrated profiles or column measurements of data products such as ozone.
So when was TOMS launched?
Well, that's been around for
Let me say
long time,
10 years, yeah.
Okay, so it's an older product.
But it'd be interesting.
Yeah, it's an
you
older
could
one.
overlap and have some. But basically, doesn't TOMS only have the nadir view, basically?
Yeah, it's only the nadir views, yeah. So its resolution is even coarser than this one. So
Yeah, so you had basically a column, you could only
look at the bulk,
you could vary the angles and
Right.
decompose your column.
Right. So you can say, ozone over here is just, I think the average is 330 or something Dobson units, so you can say it's 320 or something like this. But, the take-home message I want to just kind of reinforce is that, you have a great pool of satellite data. You have a large number of ROSAS calls, NASA ROSAS calls, that really are trying to understand, not just qualitative understanding, because we're really trying to put numbers on this radiative forcing issue and the transport of really important issues, important species such as aerosols during extreme events such as monsoon events, biomass burning events, and really integrating that with the forecasting aspect, the dynamics aspect, and chemistry is important, but also for really saying something about even localized forecasting. I think that's really one of the major directions NASA is heading, and they want to pump money into it as well. And so, so there's a lot of data out there to make sense of this.
I think you're right, Christopher. We have, I think the future is bright. Remote sensing can actually benefit engineering. The resolution is getting better and better, and thanks to NASA and GPL, we'll be able to understand much more about global warming, sustainability, pollutions, and so on. So we have a lot to do to bring the engineers to NASA and NASA to the engineers. And so the future is bright, and I think we should look forward to these changes between both parties. So if we don't have any more questions, I'd like to close the seminar. Thank you very much.
Yeah.